In this video, we're going to talk about the rate equation and exam-style questions related to the rate equation. We're now going to move on to do a most common question, level of response, which is one where you have three different things to do, usually in this type of question, and they have answers that are level 1, 2, and 3. Now, in this one, they want you to prove that the rate constant and the rate equation, okay, so there's the rate equation right there. They want you to prove that orders are correct in that rate equation. That rate equation is important. And with K, they want you to calculate it and give it to two significant figures in standard form and with units. So you've got a few things you need to do. What I'll recommend to you, because this is such a large question, is that you just stop and read. So stop the video, read it first before I continue. And of course, if you can do it, do it. So we've got chromate reacting with hydrogen peroxide under acidic conditions. So there are three reactants, and then we've got the concentrations in a table here, and then at the end we've got the rate. And we're given our rate equation. So as ever, we're going to move this to the side and put all the important stuff in bold. So we've got our important things in bold, and we're going to look and see what is actually the important information. So we've got to prove something here. We've got to prove that that is first order and that the chromate is second order. And lastly, we've also got to prove, don't forget, that that is zero order. So we have to prove H plus 0, H2O2 is first, and Cr2O72 minus, or dichromate, is second. So we've got to do that by doing as we've done in previous ones, looking at the differences in concentration and how the concentration is going up or down, and then how that affects the rate. So first of all, we'll look at H2O2 just because it's the first one in the first column. So as we go from this reaction to this reaction, we're timesing that concentration by 2. And now let's go and have a look at the rate, because the rest is staying the same. So the chromate is staying the same and the H+. So if we look at our rate, and again, if you're doing this, put it in your calculator first. And then you can see that that is times by 2. So we've got a proportional relationship. That is the sign of a first order reactant. If I times this by 2, times the concentration by 2, the rate will times by 2. Proportional relationship. And therefore, we have H2O2, and as we would put it in the exam, H2O2, the concentration is times by 2, the rate is times by 2, therefore a first order reaction, this proportional relationship. We're then going to move on to the next one. And we can see this is a little bit more complicated than our previous ones, because if I then move on, you can see I've chosen the next reaction and compare it to the third reaction. You can see there's a times 2 there, but you can also see that chromate is going from 0.02 to 0.05. So there's two changes happening at the same time. So the key here is to say, well, I already know that H2O2 is a first order reactant. I've already proved that. So I think from this change that the rate will double. Now, if I know the rate will double, I can then compare the extra change in the rate when I do this change, which is to take that up by 2.5 times. Now, as I said, H2O2 is times 2 and the rate is times 2, so that's what we would expect. So at this point, hopefully you're putting the numbers in and you've got your calculator and you're looking at the rate at the bottom. You're seeing how much is that rate increased by? Well, it's increased by 12.5 times. So let's have a look at that in a little bit more detail. If the chromate is second order, times 2.5 times would increase the rate by 6.25 times. And that 6.25 is 2.5 squared. So if you remember back to what is a second order reactant, second order reactant is a reactant where you change the concentration, and the square of that change in concentration will be how much the rate goes up by. So the change here is 2.5, which we got from down here. Okay, 2.5 squared is 6.25. So we would expect it to go up by 6.25. It's not gone up by 6.25, it's gone up by 12.5. But if you look at that, 2 times 6.25 is 12.5. And that accounts for the fact that the first order reactant is being times by 2, and therefore the rate is being times by 2. And if that's second order, it'll also be times by 2.5 squared. So we've now proved in these statements that chromate is a second order and H2O2 is a first order. That leaves behind our H+. So in our H+, we need to compare, for example, going from the second to the fourth. Now, if we're going from the second to the fourth, that's times by 1.5. And then we can see the reason we've chosen the second and the fourth reactions is because if you look over here, you can see that the hydrogen, or the hydrogen ions are going from 0.2 to 0.3. So they're also timesing by 1.5. Because they're times by 1.5, and we already know that the H2O2 is a first order, we can see if there's any change there to the rate. So again, you should be getting your calculator out and putting those numbers in, putting me on pause and having a go and seeing what it is. Now, if that is the case, and we look at the rate, we can see that's also times by 1.5. Now, if the rate is times by 1.5, and this is first order, this hydrogen peroxide is first order, so if I times the concentration of hydrogen peroxide by 1.5, the rate will times by 1.5. That means any change by the H+ ions has made absolutely no change on the rate itself. And that proves that H+ is a zero order. So if the H+ is times by 1.5 times, the rate is increased by 0 times, because the rate increase that happened was due to the fact that H2O2 is a first order reactant, as we've got up here. So we have proved with these that we have those first order, second order and zero order reactants. We're going to get rid of this answer now and try and attempt the second part. And the second part is calculating the rate constant. So we're going to calculate the rate constant and give our answer to two significant figures. So if we look, we've only taken one of our reactions. Remember, the rate constant only changes with temperature, doesn't change with concentration, so we can choose any one of these reactions and we can put numbers into our equation as long as we just go along the line. So we know that our rate equation is that, and so if we rearrange that to look at K, so K is going to be your rate, and that rate is going to be divided by your H2O2 and your Cr272 minus. Okay, and we have our rate equation right here. Now let's just make sure the orders are correct. H2O2 is first. Looking up there, I can see Cr2O72 minus is second. So let's just put that in. Now from there, we just plug our numbers in. So K is going to be equal, and we go down here and we see our rate is 2.04 times 10 to the minus 6. Okay, so that's 2.04 times 10 to the minus 6. And then we're going to divide that by our H2O2. H2O2 is 0.02. And then we've got our chromate. So our chromate coming down here, and that is going to be times by 0.02, but remember your square. Okay, so you've got your square there. Now, that changes if you put it into your calculator. Hopefully you got it in the calculator now. And you can see that that comes out as 0.255. Question though, if you go over here, it says two significant figures. So two significant figures means I need to round, and I only need two of these. So there's your 2 that you've got there. So that needs to round, and that will go 0.26. So we've got our K, and we've got our done our calculation. We need to now do our units. So the units, we go over here, and then we start saying, what are our units on this? Well, our rates units are moles, dm cubed seconds minus 1. Okay, so moles dm cubed seconds minus 1. And then let's try and fit this in here. And then we've got moles dm cubed there. Okay, so moles dm cubed. And then we've also got times moles dm cubed. Okay, but that's squared. Okay, so that's squared. Now, all we have to do, if you've done units before, is look at this and go, right, let's cancel. So we cancel out the moles per decimeter cubed. So there's my moles per decimeter cubed gone, moles per decimeter cubed gone. That leaves us with moles dm cubed squared. Now, if that's moles dm cubed squared, remember, raising it up here, okay, is like timesing it by -1. So I'm going to times that dm cubed here by minus -1. I'm going to times this moles by -1. At the same time, I'm going to times what's in the brackets by 2, because I've got a 2 on the outside. So 2 times that. So don't think of it in that way squared. Think of it like 2 times whatever's in there. So 2 times whatever in there is going to be moles squared decimeter -6, and then you times that by -1. So you get moles -2 decimeter 6, and then you have to put your positive integer first, right? Okay, so that means basically we'll go decimeters, and we'll go decimeter 6, and mole -2, and finish it off because I've run out of space. Seconds -1. So decimeter 6, moles -2. And let me just finish that off in a little bit neater because I don't like the way it comes down here. So that means your units are going to be decimeter 6, moles -2, seconds -1. So we have got our calculation of rate, which is perfect. And we've got our mark for our answer here, and we've got our marks for our units here. And that, remember, is all combined in the previous slide with proving it in writing. So really make sure that when you've got questions like this, you have to prove it in writing and then do your calculation and get your units. We're now going to move on to design an experiment to determine orders. Now, what I recommend now, big long question like this, stop the video, read the question, and then turn the video back on and I'll start to go through it. Just make sure you understand all of this before we carry on. So, we're starting with a chlorine being formed in this reaction with 3 reactants, chloride, chlorate, and H+. We are given these 3 concentrations, 0.5 moles per decimeter cubed, and we know there's a total volume of 60 centimeters cubed was used for each experiment. So that means in each experiment, we have to split these 3 reactants and make up 60 centimeters cubed. So it makes sense that we would have 20 centimeters cubed of each to add up to 60 centimeters cubed. Here we're given concentrations, okay, and the concentrations that we have to reach are 0.25. So notice we're halving the concentration for chloride here, we're halving it for chlorate in the middle, and then the H+ over there, we're halving it as well. So I'm going to show you a simple method to halve the concentrations. Now, in this question, you've got to show how the student could obtain those concentrations, and like I said, that's what we're going to do, but we also have to determine the rate equation and rate constant, and we'll come back to that in the second part of this question. So let's get rid of this table for now so we can concentrate on creating the actual different concentrations that we require. So we know it's that total volume of 60, which you've highlighted here, and these 3 concentrations we start with. So what we have to do is look to change the concentrations one at a time, and we've already done that in the previous table. And then add water to maintain the total volume when changing the concentration of the reactant. Now, what does that mean? What that means is, if you've got 20 centimeters cubed of each one, and you want to change the concentration of each one, okay, and by a certain amount. So for this time, we want to change it by half. So all we do is put half of the reactant we want to change in. So when we put half of the reactant we want to change in, we have to still maintain the total volume. Otherwise, we won't halve that concentration. For example, we add half of what we originally had, okay, and then we add the 10 centimeters cubed to bring it back up to 60 centimeters cubed. What that will do will halve the concentration of the H+. And you can confirm that with a calculation using moles equals volume times concentration, and then rearranging that so moles divided by volume which will equal your new concentration. But we're not going to do that in this video because it's not required for the actual question itself. But it's good if you stopped it and tried to do that. Now, if we look here, there's 10 centimetre cubed of each, and then we go down, we do exactly the same thing with the chlorate, exactly the same thing with the chloride. So we've now just halved the concentration each time as we've gone from 1 to 2 to 3, and we've halved an individual reactant. And so we can then see what the orders are. So that would be how we do it. But let's move on to the actual table with all our concentrations and with our rate of reaction as well. And do what we normally do, which is look at the changes. So changes here, divide by 2, and we're seeing no change in the rate. If there's no change in the rate and you've divided by 2, that means it's a zero order reactant. That has no effect on the overall rate from changing the concentration of H+. We then go to the next one, and we've got divided by 2 here, and then we've got divided by 2 here as well. So therefore, there is a proportional relationship to it, and because there's a proportional relationship, it's a first order reactant. We then go to the last one, where we're comparing 1 to 4. And again, we're all going from the simple one, because we're only changing one at a time, we can just all compare to number 1, which is what we're doing here, 1 to 3, 1 to 2. And you can see it's divided by 2 here, and it's divided by 2 here as well. So that must mean the chloride must be a first order reactant as well. So we've designed an experiment with our new concentrations, and we have then looked at what the different orders are, and now we're going to apply it to the actual rate equation itself, and then choose our different values. So we've chosen the top value because it's the easiest one to do. And then we are going to go and calculate our rate equation. But first of all, we need to have the rate equation. So we have determined this. So it's going to be rate. Okay, so it's rate equals. We know that was first order, that was first order, that was 0. So that's rate equals K Cl minus. Okay, and then ClO3. Okay, so we've got our rate equation. So from that rate equation, we can do some quick rearrangement and just say rate is going to be divided by Cl minus and ClO3. They're both first order, remember, and that is going to be equal to Rk. So we've got a rate equation, and all we have to do now is put the numbers in. So it's 0.01875. Okay, and then we look at our chlorine, 0.5, 0.5. So 0.5 times 0.5. And that will equal 0.75. So we've calculated our rate constant. We've used our rate and our different concentrations from one of our reactions. Remember, I said it many times, the constant only changes with temperature, doesn't change with concentration, so it's fine to have all of this. Now, the thing we haven't done is the units. So let's quickly do the units as well. Remember, moles dm seconds minus 1 and that's for your rate. Okay, and then we'll have moles dm and moles dm cubed. Now, if that's the case, we are going to cancel that. We've got moles dm cubed. Now that's just raising it up, times it by -1, and you will get some units on the side here because you're raising it, timesing it by -1, which means that will become decimeter cubed, and we always do the positive one first, and then moles -1, and do not forget your seconds -1. So seconds -1 because this remains from the top, easily forgotten. So decimeter moles -1, seconds -1. Okay, and that is how you design an experiment when you're given concentrations of the original, then determine the orders from the data, then calculate K, and then do your units. Our third type of LOR is about using the graph to calculate the half-life and rate constant, and it consists of a few different things you need to do. So we've got the esterification reaction here, and again, I would stop the video, read this before I go through it. It's really important that you focus on one thing at a time, so just read it and then listen. So, an experiment to determine the order of the reaction with respect to the alcohol was carried out. Large excess of the acid, and the temperature is kept constant, so therefore that means K is going to remain constant too. And explain why they used a large excess of the acid. And second thing is to use the half-life to show the reactions first order with respect to the alcohol, and determine the initial rate of reaction. So you've got quite a few things you need to do. So we're going to do one at a time. So let's move this out of the way and go for that first one. Explain why they use a large excess of propanoic acid in the experiment. I think it's really useful here to look at this in terms of some kind of form of model. So we've got loads and loads and loads and loads and loads and loads of the acid up here. You see the acid is the blue one. Now, we're going to add the alcohol. So the alcohol is not in excess, and therefore there's just a few of them. Now, at that point, we do some reaction, for example. And if you did some reaction, we're going to show that a little bit of these acid particles might go away. Okay, so we're taking a few of them away. Now the acid is in such excess that it doesn't matter. I know I haven't taken any of the alcohols away, it's just because I didn't put very many in the first place. But you can see here that those alcohols are still going to react with those carboxylic acid because it's in such excess. There's so negligible a difference in concentration that they're still going to react regardless. And because they're going to react regardless, effectively the change in concentration of the acid, because there's so much of it around, has no effect on rate. And if a change in concentration has no effect on rate, it's a zero order reactant. So if you want to investigate whether a different reactant is first order, second order, for example, you can make the other one be zero order, even if it's not naturally zero order. And you do that by putting it in a very large excess. So like I said, such a large excess means the change in concentration is negligible. Effectively, the concentration doesn't change to any large degree, and therefore no effect upon the rate. And no change in rate, the change in concentration equals zero order reactant. So you're forcing this acid to become a zero order reactant, even if it's not naturally so. And these are exam answers, so be very aware this could come up. So we'll move on to the second part, and the second part is use the half-life of the reaction to show that reaction is first order. I'm going to show you a little trick here, again, which they have put in exams, so it's really important you pay attention here. So we've got our graph, and we can see from our graph that we have to do half-life. So we're going to do our half-life. So we just go 5 to 2.5. This is what you naturally do. And then you go down, and there you've got a half-life, 110 seconds. That's not too bad. But then you try and halve it again. So you try and halve it again, and you get somewhere around about here, and you go across here, and you go across here, and you think, oh, I've got no data. Okay? Because I've got no data, I can't do the normal half-life. And then what you do, you're in the exam and you're like, oh, and you worry and everything like that, and then you just move on. So I want to show you that it's not as hard as it looks. So all you do is pick a point on the graph to measure a different half-life from a different position. So let's pick a different point on the graph. So let's, for example, go from 4. And that 34 seconds is not a half-life, it's just the time at 4 moles per decimeter cubed. So we do have enough data, though, to halve 4. We don't have enough data to halve 2.5. We have enough data to halve 4. Okay, so if we halve 4 and go all the way across here, okay, we have 140 seconds here. So the difference, okay, between those, if it's constant, it will be a first order reactant. So that first half-life is 110 seconds. The second one is 140 seconds minus 34 seconds, which is 106 seconds. So that means you have got 2 half-lives, okay, one with the 140 minus the 34, one with the 110, okay, that are roughly similar. Now remember, from a previous video, we've told you that the half-lives, even though they should be constant, they can be roughly constant. They don't have to be exact. So a difference of a few, like 4, is not important. Okay, it just has to be roughly in the right place. These are experimental data. It's experimental data at the end of the day. It's usually not going to be perfect. We're now going to do the final part of the question where you look at calculating the initial rate of reaction. So there's a couple of tricks here that I want to make sure that you don't slip up on. And the first thing is drawing the tangent. So the tangent has a nice flat bit on the top here. Usually does. Be really precise, put your ruler up against there and put the tangent from t equals 0 for initial rate of reaction and down like that. Okay, so we have done that tangent all the way down and we can see that it goes to 160 and it starts off from 5. So my change in concentration is 5 to 0 and my time is 0 to 160. So that would be 5 divided by 160. No, it wouldn't. Okay, so why wouldn't it be? Well, it's this little trick they put in every single time. There's a point where you should be doing this and looking, and you can see times 10 to the minus 3. They'll put it in there just to mess you up, to try and differentiate and make some people get it wrong. Okay, so you need to put that into your equation. So instead of being 5, it will be 5 times 10 to the minus 3. So 5 times 10 to the minus 3 divided by that difference in time over there, 160 seconds, gives us our final rate of 3.125 times 10 to the minus 5 moles per decimeter cubed seconds minus 1.